Good evening, everybody. Good afternoon to another episode of the Net.lol. I'll be co-hosting today with my other co-hosts, Brent, Dave Tucker, and Kyle Mestery. Today's esteemed guest on the show tonight is Dean Bogdanovic. He's accidental CEO and founder of Volta Networks. So we'd like to welcome you to the show. Thank you for being on today. Today we're going to talk about virtual routers and the possibilities and what's going on. Dean, you want to give us a little background, what you guys do and kind of what your role has been? And maybe as a second question, maybe get into why did you guys start Volta? What was the problem you were trying to solve,
Yeah. So thank you for inviting me to the show, and nice to meet 3/4 of you over like a web call. And Tom, good to see you again. I spent my whole life in networking. After college, I went for a job interview, ended up in networking, and never left it. So the rest is history. And since 90s, so today I've seen a lot of different technologies in networking being developed from, like HDLC, frame relay, ISDN, ATM, all of it, SNA, system network architecture from IBM, if somebody remembers, DECnet on
DECnet, Token
box
Ring
systems,
FIDI.
Token Ring, and used some weird languages to do networking called VTAM, and somehow I stuck in the networking, and throughout the whole career doing multiple different things, I was seeing that operations and management are really the hardest part in the networking, and I spent my last 10 years working a lot on programmability, management, automation. So that was one area that I've seen, did voice over IP, did routing, but always came down to management. And even there in the last 10 years, there's been a lot about talk automation and management, but the majority of the systems did not change. So it's always CLI based, and CLI is a human context based. But also, there's so much investment in the CLI. If you look at the CCIEs, JNCIEs, etc.,
Oh yeah,
they really know networking. But it is a lot about knowing the CLI of a particular vendor. And CLI usage does not scale. That's the one part that back in 2002, we tried to do a network management startup with a lot of ticker like spec and screen scraping. And that was really pain in the butt because the slightest change in the CLI output.
I think a lot of people tried that. I mean, we tried that even at Cisco to try to reverse engineer the CLI and whatnot. That's tough.
It's tough. And not only that, you have so many different micro versions and everything that this is hard. So that was the problem that I've seen throughout my whole career, that you build a product, but then to deploy it and manage the product is really hard. And
that's somebody else's problem post-sale, right? Yeah, that was the problem. That's when I met you, right? We were that was when NetConf was really starting to take off, right? That's kind of where I met you. That's and I think I was at BT then. But, it was refreshing to finally meet people who were like, yeah, programmability, or whatever we called it at the time, was the key to, and really we call that automation today, right? Or sorry, I got a fly in my room here. or automate, or it's capable of being automated anyway. And at least, and nobody's, I don't think anybody here is going to say netconf or Wu Yang or whatever is the greatest thing since sliced bread, but it's definitely a move in the right direction. It's definitely, programmable and whatnot. And now what we have today is even a next step after that, REST API, and API interfaces, that is, to devices and whatnot. Now you can see, and as part of that, in parallel with that, maybe a good segue for the virtual router conversation too, which is the disaggregation and virtualization of that at the same time. Now meeting with the, with large scale programmability. The two things really lend themselves to go hand in hand. So what is, so maybe jump into about a little bit about, what was appealing to you about virtual routing at the time too?
The whole concept of programmability is the main reason why I started Volta. If you look at the appliances that are being deployed today, they're all based on routers. If you look at the firewall, you have the layer 2, layer 3, layer 4 functionality, and if they are saying, oh, we are doing routing protocols, we can do MPLS, but it's a firewall. So they have a transport, and then there comes a firewall. If you look at the applications in 5G, like UPF or AGF, it's a router in the foundation, and then you have the 3GPP specified logic that sits on top of that. And today, each one of these elements is a separate physical box. You have people talk about service chaining, but they are stacking boxes that the packets
that's
are
the
being
physical
run
service chaining, right?
That's a physical service chaining. But you're looking into that. And why virtual routers made it interesting, it was routers are a platform that are hosting other network applications, BNG, firewall, UPF, AGF, as mentioned. And if you there is a piece of hardware, and you can virtualize and isolate control planes and management planes, and the application runs on top of that. You can have multiple applications sharing the same hardware platform.
Right.
In that case, your packet, the data plane, stays in the optimized data plane, in the ASIC, and only the exception traffic that has to be serviced by that particular application has to be exception up to that application. Everything else is staying down. If the firewall has to say, oh, here's a new routing policy, or here is a new filter.
So what's different though? Or like, you remember way back when Juniper made a thing like this, which was, a distributed route engine. Cisco had one. What's different now? What's different with the VR?
I built them. All those things that you're
They're
mentioning,
better.
I was doing it on Juniper, and I ran into all those problems while I was there.
Yeah.
So it really is the foundation. It's a network operating system is the obsoleted part. That whole piece of software, how it's designed, there hasn't been any innovation for the 20 plus years. That's the one part. The system architecture is still the same.
It's mostly the same thing.
It's and they're all done with vertical integration, with vertical scaling. If you look at their product lines, they're building bigger chassis, but the network software is staying the same.
It's the same stuff. Yeah, we actually had this conversation a couple of weeks ago where we were talking, and that was kind of the same conclusion, right? It was like, what's really new now, or is it just a remix, so to speak?
It's a remix, and what we at Volta decided is we're gonna break up the network operating system architecture as we know it, and we will make it programmable via APIs. Instead of having bunch of internal calls within the network OS that will be exchanging locally the calls. All of them will be public API for the consumption. The idea there is that you are reading and writing the state instead of saying, oh, I will create a configuration, then my configuration will change the state of the device. And that will be one model, one schema. And then when I'm reading the operational state will be another schema, and I have to figure out how to do the translation. And a long time ago in software development, we learned there's something called object orientation. I have a data model that represents my function that I want to achieve, and I'm reading and writing on the data model. So we said there is a hardware underneath, and hardware is abstracted as a set of capabilities and resources. VMware
it's interesting.
in a way easy. Yeah.
The way you just described, what you just described, you could implement that in a traditional sheet metal configuration, right? It's the key is the actual logical separation of the functions, not gluing them together tightly. So it's a looser coupling of the components, which then allows you the flexibility to, if we had built the routers we built years ago that way, it would be easy to disaggregate them or aggregate them together, and you could look at them like Lego blocks. And like you said, if you have a consistent object model, basically object orientation of this thing, of the system, you're not going to unduly meddle with things inside of that module, and it's only going to tell you about things that you can talk to, and then and so on. And it's interesting because we've spent a lot of time in the last couple of years helping network equipment vendors to containerize their functions effectively. And this is exactly one of the biggest pieces of heartburn, is that these pieces are so tightly coupled together that the actual way the whole system operates is very fragile. And being able to, if they were just defined in a more like you're saying, a more well-defined API in a less tightly coupled manner, they would be easy to pick. Like, we've achieved that with picking up like the route processor image, being able to run that on a COGS machine, right? But that's not the same as what you're talking about. That's really the whole enchilada except for the hardware, right? Except for the data plane. What the hard part is dissecting the control plane into other constituent components, right? Which is...
You also have to dissect the data plane, because the data plane is providing you a set of resources and capabilities. This is one part. The community was very much focused on modeling the forwarding elements, but based on the functionality, based on the capabilities. They did not take into the account the resources needed, because your ASIC, your forwarding ASIC, has a finite number of resources. And not all the functionalities are taking the same amount of resources on that silicon die. Now, when you are modeling, you are saying, here is I'm abstracting my Broadcom, Mellanox, Barefoot, TCOM in a set of capabilities and resources, and I'm exposing that to the higher levels. I don't care what is the specific Broadcom P4 Mellanox API. All of them have common filter or an ACL, depends how you call it, at the TCOM layer. Is pretty much the same. They are different implementations, but they're pretty much the same. And you know how you can abstract it correctly, that you can do the translation from the common API into a specific hardware API pretty straightforward. So once
as you're describing this too, I'm remembering this is exactly why OpenFlow didn't work right on existing hardware, because what you're describing is that mapping didn't work right. And it's that
on data center.
The data plane understanding, the control plane understanding what it can shove down into the data plane is as important as everything else, right? That's really what you're describing.
once you have that, then it's easy to put in different applications on top of that.
Or mix and match data planes even.
Oh, to you, you don't care what the underlying data planes are because
Yeah,
you have the data plane abstracted,
yeah.
and all the data plane primitives have a common API. And then
Hmm.
you're doing on the data plane, you are doing that translation into a common into a common API into a lower level hardware specific API, vendor
Yeah.
specific API.
And it frees the control plane to horizontally scale or whatever. As long as it can talk to the abstraction and get to the data planes, you're okay.
And
Yeah.
Dean, you guys are doing the actual capabilities exchange. That's part of you're not relying on vendors to have a common capabilities exchange right there, right? You're managing that layer.
Yes, that's our functionality, correct.
Gotcha. Interesting.
There is about 20% of the network operating system functionality that has to sit on the hardware. In the network element, in the forwarding element, there's about 20% of functionality that has to sit down near the hardware because it needs the intelligence for resiliency purposes. It needs the intelligence how to boot up, how to execute certain autonomic functions that you can, in case your control plane is not collocated, that you are not impacted by the latency of communication between your data plane and the control plane. This was also one of the OpenFlow problems. It had to send down all the information back to the controller to get calculated and pass it down. So that was
Yep.
another problem with the OpenFlow that we have, also solved and said, yeah, we know what has to be run down there. For example, fast reroute. You have to do it locally. RIP to FIP translation. You have to do it locally. You can't.
Yep.
So there are a bunch of stuff like that you have to do locally on the physical hardware, and provided with enough intelligence that it can do it. But on the other hand, that you're also not overwhelming the hardware because as the networks are getting more complex, they're running more elements. Your databases that have to run on the elements are getting bigger and bigger with more and more memory.
Yeah.
And
Remember, this was a problem with OpenFlow too, and P4 kind of solved that basically by introducing the compiler that knew the mapping, the real mapping. I mean, it's helped solve some of it anyway. I'm not saying it solved it completely, but that's what you're talking about, right?
yes,
And before we had the compiler, we had to do basically the capability mapping manually, which didn't work so well because it was always
now think, yeah,
it's a mapping function, and it was always the destination set was always smaller than the control plane was trying to push onto it. And then, we did optimizations to try to stuff it in there and all that. But in the end, like you're saying, you're trying to pump too much data into the data plane's control logic. I was thinking of another case. Sorry, I forgot while I was talking. But it was a similar thing with, oh, that's what I was thinking about too. Like, similarly, you can overwhelm the data plane. I mean, the control plane, right? Remember the early OpenFlow implementations would punt everything to the controller. And you could easily just destroy the controller if you had, one switch connected to the controller. Because you could have 96 ports come on at one point and say, hello, tell me what to do. And the controller went, whoa, wait a minute. 5 minutes later, everything was programmed.
well, even regular routers today, sometimes 20 minutes later, yeah, finally everything converged.
Mm. And that was without convergence in my example. Yeah. Of a
Yeah,
big
but
network.
here, and people say, you know what? The network operators are operating big networks. They know how to do that. And I'm like, okay, guys, that's fine. But do you know what is the magnitude of increase that the operators are talking about with deploying 5G. And everybody's trying to look at me like, what do you mean? How many more routers they're looking to deploy in their networks in the next 5 years? And everybody sort of, gets interesting, and they're saying, and they tell them, okay, they're planning to deploy, AT&T made the number public, 60,000 routers. And those will be 60,000 routers that will have provider edge capability. They will be running some set of IP MPLS services with BGP, and some IGP protocol and set of MPLS services. And they're like, yeah, but AT&T is big. So what's additional 60,000 routers for them? Yeah, well, they are operating 1/10 of that today, a little bit more than that. And then people
That's
are
a
like,
growth target. That's not what's there today. Yeah.
That's their growth target. And it's a 10x times. So if you're trying to operate 10 times more routers in your network, that means your databases that have to converge will be at least 10 times bigger.
10 times bigger, right?
They will need more CPU, they will need more memory, and how will you manage that unless you can achieve high levels of automation and programmability and some kind of an autonomic functions? You cannot linearly scale your network operation stack with the size of
Right.
the
So that means automation.
the elements that
Number
you're
one,
handling.
right?
That's
Holy
the first
automation,
step.
Batman. Yeah, it's interesting you say that too. Like the 60,000 number, where these gigantic numbers come from, and you said this earlier, the 5G vRAN deployments basically need a router for each one. So the rough math that I do in my head is the number of cell sites. You're going to do vRAN, but it's a site, and that is, if you look at any of the big national providers, just in North America or Europe, these people have 30 to 50,000 cell sites in their per country. Forget about in Asia, where that's just in a city. But and that's the kind of thing I wanted to get to the bottom of, because really, for people that are listening to understand, where does your stuff come to play and why is it important? Besides the kind of the technical stuff we were talking about, practically speaking, you really need one of these per cell site, and you can't rack a 20U box at each cell site just to do routing, because power, cooling, space, none of it makes sense anymore. You need a virtualized thing.
Don't forget the latency. This is
Latency.
a new requirement per cell site as well.
Yeah. And then operations-wise too, right? You don't want to configure a giant box for a small cell site. You don't need, like you said, you need a handful of IGP type configurations and other things, firewall, yada yada. But I mean, you don't need to rack a giant box for that. And then you talk about redundancy and HA and things like that, and having it virtualized, having the control planes virtualized for sure is a win, because you could make 12 copies of them if you feel like it, as long as you have the space to run it with maybe 2 data planes for redundancy, and off you go, right?
The other idea is also that you can, once you virtualize your data plane, I will make now comparison to VMware. You have virtualized the CPU. That was the first part. You virtualized the CPU and saying, oh, I have a hardware CPU and I have a bunch of vCPUs. And now I can assign those vCPUs to different VMs that they will be running some kind of a functionality. And then we came down to containers in order to optimize further. So in the networking, we are saying, well, I have now 10,000 virtual interfaces. I have 50,000 virtual filters. I have this many buffers, this many queues, and I have this many routing entries. Now I can start playing with it and saying, I want 500 of interfaces plus 2,000 of filters plus X number of buffers, Y number of queues associated with my virtual route processor, which is my control plane. And my IGP, my EGP, my MPLS will be using those resources to communicate. But these are completely separated. If I want to run a BGP over in a cloud over 8 virtual CPUs and give it a 32 gigabyte of RAM because I'm running a route reflector application that has to deal with high single million entries of routes and distribute them across the network, and I want to do it, have CPU and memory, I can just say, okay, I can run it somewhere in my metro area, and it's a VM running on a cloud platform, and it connects to a physical data plane there is somewhere in the network. Now, all the fast calculation, the convergence, the management is happening in the cloud because computing there is cheap. But all the forwarding and the forwarding policy execution is being done down on the hardware because the hardware knows the local conditions.
But it's also very expensive, so you only want few of those.
It's also very expensive.
Yeah.
That's very true. And this, the trade-off that you are doing and building in order to create such applications, and you can then do horizontal scaling. I can have 2 small data centers, each one running a route reflector. They can be both using the same data plane resources. They're just in an HA state.
Yeah.
Now,
it's interesting.
I will not go into details how that, but both of them can calculate exactly.
No, but they're both available and they're ready to go. Yeah.
If one fails, the other one takes over, or you can even run them in parallel. I need 8 route reflectors running on the same data plane resources. Sure.
Yeah, it's interesting. Like as you're describing this too, I'm thinking back. You remember, guys, we were talking with T-Graph about eBPF and AFXDP a couple weeks ago, and how the advantages of doing this on the NIC and offloading this. This is an interesting sort of juxtaposition from that, right? Which is like you're basically taking most of that forwarding capability out of the server. In Dean's case, where you're dedicating it in a certain place, right? Or at least the data plane, right? And the control plane, I suppose you could implement as BPF programs, etc. But can you actually? How hard is that going to be? Versus just loading a VR as control plane, which is all there. I mean, I guess that's kind of what we're talking about. Like, you could dedicate one socket to the VR in everything that it needs to run. And then the other socket is the workload stuff on the same machine. I mean, I wonder how that compares to a BPF setup. Like, practically.
When you say BPF, if you can, are you talking about Berkeley packet filters?
Yeah, eBPF and AFXDP. So moving out moving the data plane logic out, and even some of the control plane logic out onto the NIC, right? So you could move, your forwarding function. Your firewall function, you could say build in BPF and run it on every NIC, and you would run a slice of the firewall out there, and it would just run. And it was sort of like the NICs are like your data plane in your example.
That's what I'm asking you. NIC is a set of data plane resources that you abstract and expose to any application that it wants to run.
Yep. It's just that rather than considering the NIC like, n number of physical interfaces like we do today, or we VIF on top of them, the VR could, like in your VR model, you literally grab the NIC, right? It's yours, and you route.
No, it's not yours. No, that's the whole point. It's like NIC is abstracted. How you abstract a physical switch, the same way you abstract a NIC. And they provide same APIs. From the route processor perspective, you literally don't care. It's a forwarding primitive exposed to you for your usage.
Oh,
yeah.
So it's a forwarding thing.
That's right. I think what
care.
Dean's saying is you put the same control plane, just layer it over the NICs in this case, if you want.
Yep.
Yeah.
It's exactly
Cool.
the same. For
Yeah.
example, Intel NICs or Broadcom NICs, they have their own set of, in there, they have some of switching capabilities. And you're saying the same primitives that are in those NICs are also in the Ethernet switches, just at a higher capacity.
But what's interesting is that in your model, Nick, Dean, sorry, in your model, Dean, the NICs can be controlled from somewhere else too. Like the RP image can run on a server over there and control the NICs on this server over here, where the CPU is doing other stuff. Could potentially do it like that, whereas BPF is more integral, right?
Yeah.
Well, this is
Or is it?
It's where, like, the way I look at it is that it's with BPF, what we're trying to do is we're trying to push everything out to the edge, right? So we're expecting the compute nodes at the edge to be able to make decisions for themselves and have everything run inside the kernel, whichever way we want to do it. VR seems to work, any which way, right? You can have the VR run in the cloud, do its computation, and program data planes somewhere else. That's fine. I guess the only trouble you're going to have with that is potentially latency, depending on how far away your compute is from your data plane. But I think both could work together potentially. But I feel like we've got to go one way or the other. Like either we're trying to push everything out to the edge or we're not.
Yeah, it's almost
really.
kind of it's almost like an antithesis of disaggregation. So it's like we're disaggregating a little bit, but we're also saying it can be more efficient having less number of RPs out there. So like how are you dealing? Because like whenever we start saying we'll have this kind of centralized RP, well now we're control plane we start running to like float and state, and so how are you kind of managing? Is there not a lot of churn on these edge sites? Is that what you're assuming?
So we really are saying you will run as many VRs as you need. We made a physical limitation to run up to 255 VRs on a single 1U switch. So think about, you will have one line card and 255 supervisor cards controlling the one line card.
Super HA.
So, and it's completely up to you, and they're all active. They're all active. They're all controlling that one line card underneath there. And you can now start mix and matching, creating different meshes and things like that. So from that, one perspective, we are, okay, we are giving you the tools because you want to have multi-tenancy and that you can scale it. I want to go back to the server example. You can get full router functionality with local decision making on a 1U server from any of the x86 server vendors for less than 5% of CPU penalty. And you can use the other 90% of the CPU for an application like VDU. In the case of an Open RAN, you want to use those servers for Open RAN, but you know what? You need front hall gateway, cell side router, you need a bunch of functionality, and then you have a conflict. What we will be using for what? In the latency sensitive applications, we are running on that server in our software, because this is how we have broken up the network platform architecture. You have the latency sensitive control plane management application. Those are your modules, and you decide where you're running each module. And then we have a coordinator that coordinates that, and then it knows where is what and how to communicate between them, what has to be connected with what in order to provide the right functionality. So with this idea is, if you have something that has to run close to the edge, go ahead and run it there, because you will run the compute node with, let's say, I have to run, for some reason, I need my IGP functionality at a very low latency, I have to run it on a device. Fine. But I can run my BGP off the device.
Right.
And if I have a super large BGP, on a server, and the system will calculate in between correctly, and they will be all talking over the same ports. But you are distributing the load. Where's the most
Well, that's
optimal
the
port?
thing too. Like when you say your example of 255 control planes, they're not all identical necessarily. One could be a BGP process, one could be blah blah blah, this, that, the other thing, and they're all, that should also work too, right? And
Yeah.
that's another interesting way to scale, horizontal scale. Like you could run that
So
one hop
actually,
into the network even, and it would
actually,
be
there's
okay.
one thing different there. I want to put some. We are saying you have 255 management domains on that device. So if you have one IGP running down on the device and one BGP running in the cloud, they're considered, from our perspective, one virtual route processor if they are given to a one administrator. So if you can put that your BFD, BGP, ISIS, LDP, you can have them running in different areas, but they are one management domain, one
One
tenant,
logical managed domain, basically.
one managed, and this is like your one logical element, and this is considered one.
Makes
Like
sense. I just want to
OEM
make sure
stuff,
people can
all of that is,
understand,
yeah.
because it can be that granular, right?
Yes.
Yeah, I guess I
And
was
still
kind of
work.
thinking about the security of all of this, right? Because like thinking back to how virtual machines were done, like before Intel had the extensions for that in the CPU, it was all very much done in software, and there was always that risk that something which is in one VM might be able to leak into another. So I'm guessing, are we still at that sort of layer with this type of virtualization, Dean, or are we where can you draw that line? Could you safely have multi-tenancy on there?
It all comes down on, so the ASICs are the ones where you have to be very careful. But luckily, the ASIC vendors are providing you the construct inside. They're providing you that separation. There is VSI and VRF inside the ASICs that you can start then slicing up and dicing up and using as the physical separation, that what's inside this VSI cannot be inside the other VSI. They are very good at that. And it's a matter of how will you model everything correctly that and present it for consumption to the upper layers.
Where I'd be more worried, Dave, is on the NIC. If the NICs behave that way, because the NICs, until very recently, have been designed for, one server use, basically. And what you said is potentially an issue there on older NICs. But like what Dean was saying, NPUs for a long time have had VRF context in them anyway, and that's basically like what that was the wrapper around the context. And then you had to literally like route between VRFs if you wanted to connect them together. Cool.
Yeah.
Or whatever, yeah. Hey, Dean, we're up against the clock here. I want to just kind of tie things up here a bit. Do you have any, like kind of closing remarks, or like where do you think this is going to go? Where's this all headed in the near future, anyway? And kind of like what's your crystal ball saying, for all this stuff? Because that's kind of partially why people call in and listen to this thing.
So the crystal ball, the existing networking industry is a dinosaur. And I will state that there hasn't been any real innovation out there for over 20 years. And the main reason for that is that the existing vendors are protecting their business models. So it's something that it works. They know how to do that. And it's hard for them to change their business model from one area to the other area. And the disruption has to come from a new vendor. But unfortunately, the investors in the US or general worldwide view network industry as sort of a hard one, and the service providers wasting a lot of money but not executing on, with smaller companies. That's the one part. They're saying, this is my infrastructure, and as it was before, nobody will get fired for buying IBM. Now it's nobody's getting fired for buying Cisco.
Yeah.
And this is one of the
True.
problems that are out there. But I believe that the economic pressures will force the industry to change, because the appliance model that Cisco, Juniper, Huawei, Nokia, everyone is selling cannot grow to the needs that the industry needs. The 5G will be monetized by the industry complex, and there's already many industries in many countries that are saying the telecom operators will deliver us the services there that we need, or we will be asking to operate our own private 5G network by ourselves, because we just need better connectivity. We've seen how our back office applications have significantly increased the productivity because of automation, because of programmability, because of better connectivity, cloud technologies, but our front office are very hard. I have a nice example about potato chip factory. And when you ask them what is their biggest productivity problem, knives. They have to
Keeping them sharp.
not only that, they have to be, every knife in the production line has to be equidistant to each other, because when they're not cutting like one, potatoes are cutting with hundreds of knives, and they all have to cut the potato at the same potato slice at the same thickness.
Yep.
Because if it's thicker or thinner, it will overcook or undercook.
Correct.
And they
Right.
have to be the same. And every 4 hours, they're making sure and adjusting those knives manually. And it's two guys, one in the network operations center, one on the floor with two screwdrivers going, go a little bit left, go a little bit right, go a little bit left, go a little bit right. Now think about an application with an augmented reality and good connectivity there. So right now, that connectivity, the latency is too high. They tried with AR, but the latency was too high, and it was driving them crazy, because
Yeah.
until they got the feedback how much they moved too much, and then they had to go back and they threw it away. They said
It didn't work right. Yeah.
AR system that I can adjust it quickly, but that is too expensive. So those are the drivers for telecom operators to deploy 5G and help them monetize the new network investment based on that. But the money that will be paid for that is now much lower than it was back in in 10, 15 years ago. And you
Yeah.
have to see new
It's
network
more for the
reality.
same money. Yeah.
And
Well, you see
this
the
is what
commercials
makes it
on
cheaper and
TV
Cisco mobile.
today for the operators. It says, 5G at the same price as before. So they're, right. It's got a bit of an optimization to it too that we have to make work. So cool.
Yeah.
Well, thank you for joining us today. I really enjoyed this. This was, I love this stuff.
Yeah.
And I'm sure the other guys do too. But I'd love to have you on again in the future. Like I said, we barely got to the crux of it, and it took us 40 minutes. I'd love to have you on again, because this is one of those. As we do more and more of these, we find like these common threads through these different approaches to different problems, and bringing them back, I think, is really, and comparing and contrasting them, I think, is really interesting. And something folks that listen to this have told me they enjoy too. So I'd love to have you back in the future. And but thank you again for being on with us tonight. Any closing words, guys, before we wrap it up?
Oh, appreciate it, Dean. Thanks for the time. It's great meeting you.
Yeah, thanks,
Yeah,
Dean.
great meeting you too, and thank you
joining
for
us.
inviting me. And said, I love to talk about that. I spent my whole career in the networking space, so it's the it's something that I spent a lot of time thinking about and trying to find out what are the best ways in order to do that. And when you love something, it's not your work; it's a hobby. And it seems like there are plenty of us that we are having more of a hobby than a job.
Yes, sir.
We're all networking nerds here. We all love this stuff. You're right. Well, thank you again for being on, and thanks
You
again.
guys.
Thanks everybody for listening too. This has been the net podcast.lol. Thanks for listening, folks.